Okay, so we are beginning with our practical number 12, that is queuing theory, the last practical. Okay, this you will add after all other practicals had been finished. Now, about this practical, I had already explained to you what the concept of queuing theory is. I had told about the queue, the formation of queue, the length of the queue, okay, that is same as queue size. Then about the waiting time of the customers, the arrival rate, the departure rate. Now departure rate is same as my service rate, okay. Then service time etc was already explained in Monday's practical. Now I had told that it is assumed that these arrival rates or the departure rate or the service rate follows something called as Poisson distribution. Okay. Now in this case we denote it by M, a capital M. Now what is my arrival rate? See, arrival rate, and I had told that this is always represented by lambda. Okay. Now arrival rate means, I'll give you one example. If there is a system, or I'll say there is a bank, okay, so one customer arrives in a bank at every 10 minutes, okay, that is what, after every 10 minutes one customer arrives. So per minute how many customers will arrive? That is my arrival rate, okay. So one customer every 10 minutes, okay, that means per minute we have 1 by 10 customer, okay. So that is my arrival rate, okay. So lambda in this case will be 0.1, that is 1 by 10 per minute, okay. These notations are important. If something you are writing in terms of minutes, the other concepts, everything should be in terms of minutes only. If something is in terms of hours, it should be in terms, everything should be in terms of hours only. Now similarly, if it is given that from that bank the service rate is equals to is 5 minutes, okay, or I would say uh, for service time is 5 minutes, that is every customer gets served every 5 minutes, okay. So in that case my mu, that is my service rate, or also called as departure rate, service rate or the departure rate, which is mostly denoted by mu, so it will be what, 1 upon 5 customers per minute, okay. So these are my lambdas and mu, and it is assumed that this arrival rate and the service rate follows my Poisson distribution. Now, based on this, we have two models. Okay, there are many models based on this, but we will be studying about only two models. That is, first model is, it represents something like this. I will just write the notation and I will explain what it is. Okay. Now, what does this means is, now whatever is coming here, okay, the first thing, that is my arrival distribution, that is arrival rate follows some distribution that is represented by this. Now in this case it is M, that means what, M is my Poisson distribution, therefore my arrival rate follows Poisson distribution, okay. This is one of the model. Whatever comes here is my departure rate, okay, departure distribution I would say. Now in this case also, my what we had assumed, that service rate or the departure rate follows Poisson distribution. Poisson distribution, it is denoted by M, therefore it is M here, okay, in the second. Now this third one, what does this means is that this is having only one service channel, That is what I would say, one service counter I can say. Okay. So if there were two counters who would have given the service, this would have been two, something like this. Okay. So this, the third digit denotes the number of service channels. Okay. Now, next is this last one, first FCFS. Okay, I had explained this, first come first served. Okay, so this is one of the serving method or the service method. So this can be called as first come first served. So in a short form, this is same as first in first out. So one and the same. You can write this as FCFS or FIFO. It is one and the same. Okay. Now this remaining, this fourth one. Now this represents the capacity of the system. Now, this is infinite capacity in this model. That means what? The infinite number of customers can come into the system. There is no restriction on the number of customers. Okay. Now suppose I'll give you an example. Now, for a petrol pump, any number of customers can come. It is not like at the max only 50 customers, only 10 customers are allowed to stay in a petrol pump. Yes, I can agree. There is a limit on the number of service channels, but there is no limit on the number of customers arriving. Okay. Similarly, at a bank, something like this. Okay. But let's see an example of an auditorium. Okay. In that auditorium, only those number of people will be allowed who have bought the tickets or the number of seats are available. Okay, so that is what the capacity of the auditorium is finite. Okay, so in that case it will be something like that, like this will look something like this, m/m/1, that is n is some finite number, that is this n is the finite capacity. So we are going to study only these two models. This will be my model 1, that is a model which follows, whose arrival rate follows Poisson distribution, whose departure rate follows a Poisson distribution, which has only one service channel with infinite capacity, and first come first service rate. Okay, and my second model is similar model with arrival rate following Poisson distribution, departure rate following Poisson distribution with one service channel but with a finite capacity and following this first come first service rule. Okay, these are the two models we will be studying here in this. Okay, but for both, all the notations are same, that is lambda, the arrival rate will be always denoted by lambda, the service rate will always be denoted by mu. Okay, so we'll see how the things have been processed. Now, for the, now if I'm starting actually with the practical, that, so you know how to write this practical number 12, on this side date, on the other side, and the title queuing theory, and the title is queuing theory in the center. Okay, now we are starting with the first model. The introduction you need not write into the journal, write only whatever is available on the screen here. Okay, let's start with this. Now model 1, mm1 infinity FIFO, that is what, this is the model with the arrival rate and the service rate following Poisson distribution with one service channel and infinite capacity with the first in first out service rule. Okay, now if we go to see, as usual my formulas I have just listed out here. Now arrival rate is my lambda, that is the universal notation for this part. Then departure rate is same as service rate. Okay, that is denoted by mu. My traffic intensity, I have just brought a new term, that is traffic intensity denoted by rho, that is my lambda by mu. Okay, now these were just the notations. Now my formula starts with here. The probability that the customer has to wait. or the service server is busy. Now I had explained when the server is busy or where the limited servers are there or limited service channels are there, then only a queue will be formed. And a queue will be formed is same as the customers has to wait. Okay, the queue is formed, then the customers has to wait, or when the customers has to wait, a queue of them is formed. Okay, so I can even say that probability that customer has to wait or the server is busy or the queue is formed, that is it will be same. Okay, the probability that if it is, the question is stated like this, that find a probability that a queue is formed in the system or there is a queue in the system, then you will have to write this formula, that is lambda by mu, that is same as my rho. Okay, lambda arrival rate will be given, the departure rate or the service rate will be given, and will be mu. Okay, now in these cases, once you understand what kind of example it is or what the question is all about, rest is only putting the formulas and substituting the values. Okay, so it is actually very easy. Now, probability that probability of number of customers has to wait. Okay, sorry, I'm so sorry for this. Probability that no customers has to wait. Okay, now this is obvious, that probability that customer has to wait and customer does not has to wait are two, uh, I would say, the two kind complementary events to each other. Okay, so obviously the probability of this customer has to wait will be 1 minus the probability that the customer has to wait. Okay, that is the probability that no customer has to wait will be 1 minus the probability of that the customer has to wait. So it will is given by 1 minus lambda by mu, and lambda by mu is my rho, therefore it is given by 1 minus rho. Okay, now third is the q probability that the q size is greater than n. Okay, or I would say the question can be even like this: find a probability that there are more than n customers in the system. Okay, so it is same as probability that the queue size is greater than n, and in this case it is given by lambda by mu raised to n. N is any number, that is like rho raised to capital N. Okay, now fourth one is expected or the average number of customers in the system. Okay, that is the expected number of customers, average. Expected number is same as the average number, or it is same as the mean number of customers, or customers, units, individuals are one and the same terms. Okay, so it is given by rho upon 1 minus rho. Okay, then the expected number or the average or the mean q length is what? Rho square upon 1 minus rho. Okay, you will be clear with these terms when we will be solving the examples. Okay, expected or mean or the average waiting time in the queue. Waiting time in the queue, rho upon mu minus 1 minus rho. Okay, and expected waiting time in the system, that is 1 upon mu minus lambda. Now this is about the finding the waiting time probability that waiting time is more than w. Okay, now you might have remembered the example which I had given, that two students are performing a project. Okay, and the other students are performing a project, I would say, are giving a seminar. Okay, and the rest are waiting to for their turn. Okay, so in this point, the waiting time in the queue was 10 minutes, and the service time, that is the presentation time, was of 5 minutes, but the 10 minutes was excluding the service time and the waiting time more than w, that is when the project was given, that time 5 plus 10 total 15 minutes was the time which was including the service time. Okay, so there was a difference between excluding the service time and including the service time. This term I had explained in the class. Okay, so now if the question arrives, find a probability that a customer has to wait for more than 10 minutes. Okay, excluding the service time, or if something like this, probability that a customer has to wait in a queue for more than 10 minutes. Now in a queue, waiting in a queue means what? The service rate is not included in that. Okay, so that means what? After waiting in the queue, once that task has been finished, then he is going to perform the service. Okay, so this is the term of excluding the service time. Okay, so in that case it will be 10 to infinity and this formula further. Okay. And similarly, for including the service time, this formula has been given. We'll see one example from which you could be clear. Okay. Now this for very first example. Okay, before moving that, you have to write all this one, two, and this third slide into the your journals as your theory part. Okay. Now, now this from here my problem starts. Now, a problem states question 1, a telephone booth with Poisson distribution arrival spaced 10 minutes apart on the average and exponential call lengths averaging 3 minutes. What is the probability that an arrival will have to wait for more than 10 minutes before the phone is free? Now, I'll start with this. See, there are four sub questions under this. Let's see for the first one only. Now, what does your statement says? A telephone booth with Poisson distribution. So it is clear that it is of the model 1, that is what? MM1. Now, since we are already studying this under model 1, but it is given that it is Poisson distribution. Okay. So arrival rate follows Poisson distribution, and and it is also spaced 10 minutes apart. That is what? Arrival is spaced 10 minutes apart. That means what? Every 10 minutes, one customer arrives. Now, every 10 minutes, one customer is arriving. That means what? For what? Okay, I'll just write this. You need not write this in these terms as such. Every 10 minutes, one customer. So, as I explained, it will be what? Every minute, it will bring zero point 0.1 customer or 1 by 10 customers. Okay, so that will be what? My arrival rate will be 1 by 10 per minute. Okay, or zero point 0.1, whatever is easier you can write. 1.1 by 10 is also fine. Now, what is the service in this? Service is making a call. Since it is a telephone booth, the service is of making a call. Okay. Now it is even given that it has the exponential call lengths. Now I had told that the exponential and the Poisson distribution, that is one and the same. Okay. It is referred to as vice versa. So exponential call lengths averaging 3 minutes. Now what is my service? The call. And call lengths is what? The time for each service. Okay. Now what it is given that for one customer to be served, it requires 3 minutes. Okay. Now 3 minutes for one customer. So for 1 minute, how many customers will be served? Okay. 3 minutes for one customer. So for one in within 1 minute, 1 by 3 customers. Okay, so my departure rate or the service rate, departure and service rate is one and the same. A service rate, and that is denoted by mu, is equals to 1 by 3 per minute. Okay, now since both are in minutes, arrival rate as well as the departure rate, I did not convert it further. Okay, if something was within hours, I would have been brought to it to minutes or the minutes to hours, whatever, but it should be, both should be in one unit. Okay, now Let's move to the first problem or the first sub question. What does this sub question states? That what is the probability that an arrival will have to wait more than 10 minutes before the phone is free? Now, before the phone is free, that means what? He will wait, and once the phone is free, he will make a call. Okay, and that is what he will wait for 10 minutes, and then the phone will be free, and then he will be served. Okay, so that waiting time before the phone is free does not include its service time. Okay, so this is kind of the example in which you have to calculate the waiting time, the probability of the waiting time of more than 10 minutes, excluding the service rate. Okay, so I would say we need to calculate this. Let's look for this formula number 8, that is probability of waiting time is greater than or equal to 10 in this case, excluding the service time. Okay, so it will be what? You know your lambda value, you know your mu value, you know about e and all. So what you will do, you will just substitute in these formulas, you will integrate it, and you will get your answer. Okay, so I just solve this. So from here, my first one is probability that waiting time is greater than or equal to 10. Okay, and this is what? Excluding the service time. I hope the concept of why excluding the service time is clear. Okay, so now this is given by what? 10 to infinity, and I have this formula, lambda 1 minus lambda by mu e raised to minus mu minus lambda w dw. Okay, so now from here, what I will do, I know my lambda values, I know my mu values. My lambda is what? 1 by 10. Okay, 1 minus lambda is what? 1 by 10. Mu is what? 1 by 3. Okay, e raised to minus mu is what? Mu is 1 by 3 minus lambda, that is 1 by 10 w dw. Okay, this just I have simplified, so it will be what? 10 to infinity 1 by 10, and what does this comes to? This is 3 by 10, so 3 by 10 will be 10 minus 8. Okay, so it will be 7 by 10 e raised to minus, it will be what? 10 minus 3, 7 by 30 w dw. Okay, now this is a constant, this 7 upon 100 this will be. Okay, so this is a constant, I can take this out, so it will be what? 7 upon 100. Okay, and whatever it remains, I will just integrate it. Now integration of e raised to ax with respect to x is what? E raised to ax upon a. Okay, so what I will do is e raised to minus 7 by 30 w upon minus 7 by 30. Okay, and it has some finite limits going from 10 to infinity. Yes, this is the normal integration which I have performed. Now how it will be? It will just simplification will be 7 by 100 into what is this? 30 by minus 7 into what is this? For the e raised to, okay, I will substitute for infinity in place of w. Now, substituting infinity in place of w will be what? E raised to some minus infinity. Now we know it is e raised to minus infinity will be what? 1 upon e raised to infinity. Now e raised to infinity is 0. So 1 upon 0, sorry, 1 upon e raised to infinity, sorry, I'm sorry, 1 upon infinity is infinity, so it will be 1 upon infinity, and we know this goes to 0. Okay, so first term will be 0, so it will be something like this, 0 minus minus the second. It will be what? E raised to minus 7 by 30 into W. Okay, so here in place of W, I will substitute for 10. Okay, the lower limit. It is e raised to minus 7 by 30 into 10. So it will be something like this. E raised to minus 7 by 30 into 10. So this is my final answer. I will just simplify this. That is what? Cancelling this 7, cancelling this 7, cancelling this 0, cancelling this 0. This plus with this plus, sorry, this negative and this negative sign gets cancelled. This 10 and this 0 gets cancelled. It is what? 3 by 10 into e raised to minus 7 by 3. Okay. So this is my final answer for the sub question 1.